Okay, so today I'm going to continue talking a little bit about the relationship between heat work and enthalpy. And then we're going to move on into calorimetry, which is the technique that we use to measure heat, the flow of energy, thermal energy between one region and another space. So let's take a look here. I'm going to come over to the Alex. Here we go. All right, let me share this one. Okay, so in this problem, what we're going to do is we're going to relate this idea of enthalpy change of delta H. We're going to relate it to the mass of either a reactant that we're using in a reaction or the mass of a product that is being generated in a reaction. So the title of this problem is Calculating the Heat of Reaction from Molar Reaction Enthalpy and the Mass of a Reactant. Okay, so the mass of the reactant is given. A chemist measures the energy change delta H during the following reaction. 2Fe2O3 solid is converted into 4FeO solid plus O2 gas, and delta H for this reaction is 560 kilojoules. Sometimes the units, when you look at these problems, whether they be in a textbook or on Alex, some of the textbooks will put the units as kilojoules per mole. So just be aware of that. It's not an particularly important issue. It's just a detail of how they want to report the information. So use the information to answer the following questions. One is the reaction endothermic or exothermic? And then they give you a mass, 54.1 grams of Fe2O3 react. Will any heat be released or absorbed? And then if you said that heat will be released or absorbed, how much? Calculate how much of the heat will be released or absorbed, and then round it to 3 significant digits. Okay. Well, the first two questions really are, in a sense, the same question, just different wording. So the reaction is either endothermic or exothermic. For that, the thermochemical equation, we just look at the sign of delta H, right? So if delta H is positive, it's endothermic. If it's negative, it's exothermic. So in this case, it is endothermic, right? Because the positive sign, 560. And then the meaning of endothermic versus exothermic is whether it's absorbed or released. So if the reaction is endothermic, it is going to absorb heat from the surroundings. Okay. So, got a little thing here. Okay, so the first two questions are pretty basic issues. It doesn't matter how many grams of Fe2O3 is reacting. It could be 1 gram, could be 1,000,000 grams. The reaction is still an endothermic reaction, so it will absorb heat. If you said that heat will be released or absorbed, oh, by the way, there are two cases where the answer to the second part could be no. And that would be if delta H is 0, which, generally most reactions, come over here. Let me stop the screen share. There we go. There we go. So almost all reactions are either endothermic or exothermic. It's relatively rare that you find a reaction that has no energy change. It wouldn't probably happen if there wasn't any energy change. And then the second case would be that if it was 0 grams of Fe2O3, if 0 grams reacted, that means there is no reaction. Then you would say no heat was released or absorbed. But if there's any amount of reactant, there's going to be a reaction. Okay, and you'll have a delta H value. Now, the issue is, how do we calculate how much? So what we're given the mass, 54.1 grams of Fe2O3. So they're giving us the grams of Fe2O3, and we're asked to find what delta H is. Okay, we're asked to find how much heat is absorbed. It would be absorbed in this case, right? Because this is positive, right? If this were negative, it would be released. So it's a straightforward stoichiometry problem, as we covered back in chapter 3, where you're given the mass of a reactant, you convert it to moles to figure out how much you have. And then what we're going to do is we're going to relate this delta H, this value 560, relates to how much of each of those substances we have. So, right, it makes sense, right? Imagine this is a certain amount of energy that you could release from a reaction. Now, obviously, this one's positive, so it's absorbed, but the same idea. If I had 1 gallon of gasoline and I burned it, there's a certain amount of energy that's going to be released. If I have 2 gallons, it's going to be twice as much. So what we're doing here is we're relating the 560 kilojoules to 2 moles of Fe2O3 or 4 moles of FeO or 1 mole of O2. So see how, just like we did back in chapter 3, we're using these coefficients as moles so that we can have mole ratios, okay? That's often why they want to put kilojoules per mole, to indicate that this 560 is the amount that you would get, 560 kilojoules, if it were not 2 molecules, but 2 moles of Fe2O3. So that's why they'll put per mole there sometimes, okay? All right, so let's take a look at this one. It's pretty straightforward. It's 54.1 grams of Fe2O3. So we have 54.1 grams of Fe2O3, which is iron 3 oxide. This is essentially the main component of rust. So iron is, like most materials, like most elements, reactive to oxygen. It's also reactive to water. So what happens is, over time, oxygen in the atmosphere will react with iron. So if you have a piece of steel, steel is primarily iron. There's some carbon in it as well, generally, maybe some other metals. The iron at the surface will eventually react with the oxygen. It happens much faster if you put water, if you dunk it in water, or if it's very humid, but it's a pretty slow process if it's just oxygen. But it will react with oxygen to form this reddish brown color. So if you ever see rust, right, that's Fe2O3. That's a surface of Fe2O3, which provides a kind of protection for the metal on the inside. So sometimes we might think that, oh, it's bad for a piece of metal to rust, but actually on the outside, if it's just rusting on the outside, it's protecting, it creates a layer that protects the inside. So if you can keep the oxygen and water from getting on the inside, it's not necessarily a bad thing to have a rusty piece of metal. Okay, so let's write the equation down again. It's 2 Fe2O3 solid being converted into 4 Fe solid plus 3 O2. Okay, I'm just sort of doing that. And then our delta H, I'm sorry, I didn't write this down here. Delta H, I think it was 540, right? 560, sorry. Okay, so that's our thermochemical equation, right? The thermochemical equation is the balanced chemical equation and the value of delta H. Now, the meaning of this, the interpretation of this thermochemical equation is this. We use the coefficients to relate to each other, but we also use the coefficients to relate to this value of delta H. That's essentially the logic behind this thermochemical equation. So what we're really claiming is, if 2 moles of Fe2O3 react, okay, so I'm using that coefficient 2. The meaning of that is that we will get, I'm sorry, we will not get, I'm going to use an equal sign. That is associated with 560 kilojoules of enthalpy change, which again, enthalpy change at constant pressure is merely the heat that is either absorbed or released in the reaction. So see how I made a conversion factor here. I made a an equation, quality there, right? So just like we would do with the moles of reactants and moles of products, we do the same thing with this delta H. That's the interpretation of the thermochemical equation. When 2 moles of Fe2O3 react, not only will we get 4 moles of Fe and 3 moles of O2, we will also have a certain amount of energy absorbed, and that is 560 kilojoules of energy in the form of enthalpy. Okay, so now that allows us to do a conversion factor. The question is, how much heat is absorbed? When 54.1 grams of Fe2O3 react. Okay, well, pretty straightforward. So what we're going to do, since this is in moles, we're going to convert our mass of Fe2O3. We're going to convert it into moles. Right, so how do we do that? We divide by the molar mass. Right, so if you divide by the molar mass, it'll give us moles. And then we have a relationship here. So then we can multiply that by the amount of kilojoules, the amount of heat that's going to be really absorbed. I keep saying released because most reactions that we look at are released, but this one is absorbed per 2 moles of Fe2O3. Okay, so look at the logic of this. What you're doing is you're saying, hey, we got 54.1 grams of Fe2O3. So if we know how many moles that is, which we can calculate pretty easily, we can say there's a relationship. Every time 2 moles of Fe2O3 reacts, this is how much heat is absorbed. Okay, so we're going to multiply that by 560 over 2. So the molar mass of Fe2O3, well, it's 2 irons, so 2 times 55.85. And then there's 3 oxygens, so 3 times 16.00. And that's going to be in grams per mole. So it's what is 100 and about 160 or so. 2 times 55.85 plus 48.00. And yeah, it's about 160. 159.70. Remember, that's in grams per mole, right? So now we take our 54.1 grams and then divide that by, right? So 1 mole over 159.70 grams, right? That's how we're using in dimensional analysis. Okay. So that's going to be about a third, right? 50 over 150 is 1/3. 5 over 15 is 1/3. 1/3 is about 0.33. So we should get somewhere around a third. 54.1 divided by 159.7. And yeah, it's pretty close to a third, actually. 0.33876. And then the units are moles. Okay. So now you got your moles, and every time 2 moles of Fe2O3 react, this is how much energy is absorbed. So the last step would be 0.33876 moles, and then we're going to multiply that by 560 kilojoules per 2 moles. Okay, there your moles cancel, and so times 560, 3 significant digits, so 190. And that's kilojoules. And that's most likely going to be in the form of heat absorbed. So we haven't talked much about endothermic reactions because they're not really as exciting as exothermic reactions. Explosions are exothermic. Energy generation is exothermic. But there are many cases where endothermic reactions are very important, particularly in biochemistry. So 190 kilojoules of heat would be absorbed during this process. Okay, absorbed from the surround. Where does it come from? It comes from the surroundings, right? So you got some reaction here. So heat is going to come in, and that's called an endothermic reaction. Okay. About 190. Let's see another example. Oh, they're all react. I thought they might give you one where a certain amount of is produced, a certain amount, but they're all reactions. So they're all pretty much the same type of problem. Cl2 reacts. Okay, yeah. Well, let's look at a combustion. Let's do one more. Let's look at a combustion. Okay, so in this particular example, they're combusting propane. Oops, that's a liquid. There we go. Sorry, I could barely fit that in there. So delta H is negative 2220. And then they ask you, is it endothermic? Versus exothermic. So that's obvious, right? If it's negative, it's exothermic. So we know that one. That means the energy is going to be released to the surroundings. Okay. Then they tell you that you have 95.7 grams of C3H8 react. And they ask you, is heat going to be absorbed or released or neither? Well, again, as long as there's a value here, as long as this is not 0, and as long as the amount of reactant is not 0, then you're going to have some exchange of energy. And in this case, it is in the form of heat. So it's negative. So that means it's exothermic. So that means energy is released. So that's pretty obvious. And now they'd ask you to calculate calculate Q. Q is the heat released in this case by the reaction. Okay. So let's take a look at it. So we have 95.7 grams is C3H8. Now I'm going to divide that by the molar mass immediately. 1 mole of C3H8. Here I'm actually putting the chemical formulas in there because I'm kind of going through this one a little quicker. So C3H8, well, 3 times 12 is 36. 1 times 8 is 8. So that's 44. But the carbon and the hydrogens are 0.01. So 44.11, right? Because you have 11 atoms and you're adding 0.01 times 11. So it looks like it's 44.11. Okay, so what that's going to do is that's going to give you the number of moles, right? You divide by the molar mass to get the number of moles of the substance that you're interested in. So 95 divided by 44, well, 2 times 44 is 88. So it's a little more than 2. You have a little more than 2 moles. So 95.7 divided by 44.11. Yeah, a little more. So 2.1696 moles of C3H8. And now we have our relationship here. The relationship is that every time 1 mole, right? That's a 1. Every time 1 mole of that reacts, the amount of energy that's released in the form of enthalpy is that number right there. Okay, so I'm going to take our 2.1696 moles, and I'm going to multiply that by negative 2220 kilojoules for every 1 mole. All right, it's 1 mole of C3H8. Okay, so 3 significant digits. So times 2220. So it's about 4,800. Now, here's the issue. If we have 3 significant digits, we can't just put the decimal point after that second 0. That would suggest that it's 4 significant digits. So it's probably best to put it into scientific notation. So 1, 2, 3. So 4.80. Now you can just round it to the number of significant digits you want. That's one of the advantages of scientific notation. We moved it 3 positions, so 10 to the 3. And that would be kilojoules. Okay, so there's your 3 significant digits. That's probably the best way to do it. Okay. I mean, 10 to the 3, kilo is 10 to the 3 also. So 10 to the 3 times 10 to the 3 is 10 to the 6. So you could also say 4.80 megajoules. And you will see that out there. You'll see megajoules out a little bit, but it's more common to just put it in scientific notation and leave it into kilojoules. Okay. All right. So there's a couple of examples of that problem. Let me close this one out. Okay. Oh, yeah, right. I was thinking there was one more problem we have to do, but actually that comes up later. So now we're ready to talk about calorimetry. So let's talk a little bit about calorimetry. So this is section 5.4. Okay, now the term calorimetry essentially means measuring heat. Metry means measure. Caloric, that means heat. So we're really just measuring heat. That's the idea here. Okay. I'm going to start by considering a block of copper. Okay, block of copper. And I'm going to give it a mass of a gram. 1 gram, right? Relatively simple. And I'm going to give it a temperature of 20 degrees C, nice room temperature. Okay. Now, here's what we can do experimentally. There are nice, precise ways to do these measurements using electricity. What we can do is we can transfer energy to the copper. There's different ways to do it. You could do it through electricity. You could do it through putting it in an oven that is regulated at a temperature. So let's imagine we do this. Let's imagine that, we've got it in this container, and the container is really nicely controlled temperature. And what we do is we add some energy. We add energy to the copper in the form of heat. And the temperature changes. The temperature of the copper goes from 20 to 21. I guess just to be kind of like consistent with Alex, I'll put the decimal point there. So it goes from 20 decimal degrees Celsius to 21 decimal degrees Celsius. Okay, degrees Celsius is a common temperature scale we'll talk more about when we get to chapter 10. It's a temperature scale based on the idea that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Okay, so what was our change in temperature there? We have a change in temperature, right? We went from 20 to 21 by adding heat into the copper, by transferring energy into the copper. Okay, so it might be a good idea to label these with subscripts as initial and final, right? Our initial temperature was 20 and our final was 21. So let's calculate the change in temperature. I'm going to call that delta T. We did this with volume last time. So the change in temperature is the final temperature minus the initial temperature, I for initial. Okay. Now, I want to point out that different people will use different notations. So I don't particularly like I and F, but that's fine. Initial and final, it kind of makes intuitive sense, right? Sometimes people will use a 1 and a 2. Okay, 1, 2, right? And then some people will use, the physicists are fond of this. You use a little 0 for initial, and then you use a 2 here. Okay, so for example, I could write the initial as Ti or T1 or T0. Okay, initial is a 0. These are all subscripts, right? And then this would be TF or T2 or T, actually typically if you're using 0, they'll use a 1 here. So T1. Okay, and there are others as well. There's other conventions, notations that are used. Okay, whichever one you want to use is fine. I'm going to use final initial for now. When we get to gas laws, I might change to 2 and 1. Okay, so that's our change in temperature. So let's calculate it. Okay. 21 minus 20. Right? So that's a nice round number, right? 1 degree C. We change the temperature by 1 degree C. Okay. Now what I'm going to claim, this is my claim. The heat required for this change is 0.385 joules. That's my claim. That if we have 1 gram of copper and we change the temperature from 20 to 21 degrees Celsius, the amount of energy, the amount of heat required for that temperature change is precisely 0.385 joules. Okay. Now, I'm going to do exactly the same experiment, but instead of using copper, I'm going to use water. So I'm going to have a gram of water. Now, water at 20 degrees C is a liquid, right? So I'm going to draw it kind of like as a blob, right? Like a water drop or something. And again, the mass, I'll use a symbol now, is 1 gram. Our initial temperature is 20 degrees Celsius. And we're going to add some energy to bring the temperature of the water up to 21. That's not a very big change, right? I'm not sure you could detect that with your senses, but maybe you could, I don't know. So what is, again, delta T is the same, right? So delta T is just going to be 1 degree C, right? Because it's 21 minus 20. And now here's my claim here. If this is 1 gram and our temperature changes from 20 to 21, the amount of heat required for this process, the amount of heat that we had to add to the water in order to make it change its temperature, is 4.184 joules. And we're using the units joules here, right? There are other units of energy out there. Okay, so notice it's a big difference, right? In fact, it's about 9 times as much for water as it is for the copper. And so what we're going to do is we're going to claim the following, that for each substance that we have in nature, so that would be the elements, copper, gold, oxygen, beryllium, each substance, then we have compounds like water, ethyl alcohol, alanine, whatever substance whatever substance we're talking about, each has some sort of quality about them that affects how much energy is required such that that substance changes temperature by some given amount, meaning that it takes over 4 joules of heat to make water change by 1 degree C, 1 gram of it, whereas it only takes about 0.4 joules of heat to make this piece of copper change by 1 degree C, assuming the masses are both 1 gram. Okay, so there's some quality, inherent quality about all substances that affect how much heat it's required to make it change temperature. And we call that quality specific heat capacity. Now, typically, since that is a mouthful, specific heat capacity, we generally just call it specific heat. Okay. And unfortunately, there are different symbols used for this. Your textbook by Burge uses an S, a lowercase s for specific heat. Your Alex uses the more common symbol, which is a lowercase c, which I believe is a superior symbol to use. So I'm going to go ahead. All right, it's either S or C, lowercase c, but I'm going to focus on C. I'm going to use that from now on. Okay. So the specific heat of a substance is essentially the amount of heat required to raise the temperature, I'll abbreviate temperature, temp, of 1 gram of a substance from 20 degrees C to 21 degrees C. Okay, that would be a definition of the specific heat. You have to be careful about these definitions. They change sometimes based on what people are measuring, how they're measuring things. As they develop new techniques for measuring things, they come up with new ideas of definitions. So what we're going to claim is that even though it's defined from 20 to 21 degrees C, it's more universal than that effectively. So the specific heat going from 30 to 31 would be the same as it is for 20 to 21, or 10 to 11 would be the same. Okay. So even though it's defined for 20 to 21, typically we just say a change of 1 degree C, right? Okay, so as long as it goes up by 1 degree C, we can use that specific heat capacity. And there are tables that you can look up for values of specific heats. So let me show you. Thank you. Let me show you a few values of specific heats. Now, the units are variable, but we're going to use joules per gram degrees C. The term specific generally in the sciences means per gram or per kilogram per mass unit, but you can also have molar specific heat or molar heat capacities. So it could be per mole. For the most part, we're going to use specific heat, which is joule per gram degrees C. Okay. You may see Kelvin also. And we haven't really talked about Kelvin yet. So it could be joules per gram Kelvin. For our purposes right now, we'll get into this in chapter 10 in more detail. It's the same thing as degrees Celsius for reasons that we'll go into later. Okay, maybe in an example, I'll show you why. Okay, so here's a few. We have copper, right? So copper. Now, it turns out the state of matter is important. The atmospheric pressure is important, and all these, there's different variables, but here's a value, 385, and the unit's joules per gram degrees C. Water, liquid water, is 4.184. Okay, so let me see if I can, what I'll do. You have to be careful when you look these things up because you have to be careful because again, there's many units that are used for these things. So if you don't have the right units, it could be confusing. Okay, so here's a few. So we're going to focus on the left side, which is specific heat capacity, right? For select substances. There's quite a few in this table, right? About 20. So air has a specific heat. Air is 1.012. Again, the units are joules per gram degree C. Aluminum, about 0.89. Argon, about 0.5203. Copper, 0.385. I'm glad I remembered that one right. Granite, right? A stone. See, it can be pretty, any substance has this specific heat, 0.79. And graphite, which is pencil lead, is 0.71. So not that different from granite, right? Helium, 5.19. That's a lot, right? Helium's a gas. So is air. So is argon. Iron, 0.45. Lead, 0.129. Textbooks in general chemistry will generally have a lot of metals and then water or maybe alcohol. So water, notice ice is different, right? 2.09. So ice has a different, but that's at a different temperature too, but has a different specific heat. Water, 4.184. Steam is 2.03. This is a nice table, actually. Titanium, 0.5. So one thing I want to draw your attention to is that metals in general are less than 1. It's relatively rare to have a metal greater than 1. Are there any? Well, lithium does, strangely enough. I don't know why lithium is 3.58. I'm not sure I even believe that, to be honest with you. Sodium is 1.228. Steel, 0.44. Titanium, 0.5. So most of the metals in here are under 1. I am kind of curious about lithium. Let's make a note to myself to look up lithium. Okay. Water is by contrast is quite a bit larger. It's over 4. Okay. So water has a large specific heat. I'm not going to go into reasons why, but it has to do with the molecular structure of substances. Okay. So let's take a look then at turning all of this discussion into an equation. Okay, so we have delta T, right? That's our change in temperature. We talked a little bit about that. We have mass, right, which is M. Actually, let me be a little bit more formal about this. I'm sorry. So let's define everything. Change in temperature. Which is T2 minus T1 or T final minus T initial. See, I go to 1 and 2 very quickly. Okay, which is delta T. We're going to call that delta T. Okay. Then we have mass. And the symbol for that we're going to use is an M. And then we have heat. And the symbol we're going to use for that is Q. And then we have specific heat. And since I have enough room here, remember, it's really specific heat capacity. And that has a symbol C. Now, for the most part, the units we're going to use here are degrees C, grams, joules, and then joules per gram degree C. This one actually has 3 units in there, okay? And now what I'm going to do is I'm going to put all 4 of those quantities into an equation, and it's going to be called the calorimetry equation. I guess you could call it that. Q is equal to M times C times delta T, and that's the calorimetry equation. Now, again, for the Burge textbook, what they're going to do is they're going to write it this way. Q equals S times M times delta T, where S is equal to the specific heat. Okay, that's the only real difference. Now, there's actually a logic to putting the S before the M. In equations, we often put the constants first and then the variables after. So putting the S before the M kind of makes sense. MC delta T it's kind of written historically. It's an old equation, and so it's written that way. We could do it Cm delta T, it doesn't matter as well, but typically it's written as Q equals MC delta T. And the interpretation of this equation is, this is an equation. So now we have a relationship between heat and specific heat. We have a relationship between heat and mass. We have a relationship between heat and change in temperature. And what this says is it requires a certain amount of heat, energy, to change the temperature of a substance. And the amount of heat depends on the specific heat capacity, C. It depends on how big the temperature change is, delta T, but it also depends on the mass, right? So if I want to heat up a swimming pool full of water, that's going to require a lot more heat than a thimble full of water, right? So M is very different in those two cases. So Q has to be very different. Okay. And that's called the calorimetry equation. That allows us to do all sorts of equations, all sorts of calculations. We're going to use it quite a bit. And in one of the first problems on ALEKS, what they actually ask us to do is they give us the information except for the specific heat, and they ask us to find the specific heat. So there's your equation, Q equals MC delta T. There we go. So let's take a look. I'm going to look at an example. Oops. Sorry. Calculating specific heat capacity. A chemist carefully measures the amount of heat needed to raise the temperature of a 878.0 milligram sample of pure substance. It's not telling you what it is. From 56.3 degrees Celsius to 68.2 degrees Celsius. The experiment shows that 49.1 joules of heat are needed. What can the chemist report for the specific heat capacity of the substance, and then round your answer to 3 significant digits? Okay, so if you take a look at this, let's see if I can zoom in here a little bit for you. They're carefully measuring the amount of heat. The mass of the substance of the sample is given right here. So there's your mass, M. Now do notice it's in milligrams. And what I said was our answers need to be in grams. So that's typically the case. But here's your temperature, right? It's going from 56.3 degrees Celsius to 68.2 degrees Celsius. So there's your temperature change, right? T2 minus T1. The experiment shows that 49.1 joules of heat are needed. So that's your Q. So really what you have is M, your 2 temperatures, and Q, and they're asking us to determine the specific heat capacity, right? So that's at a C, lowercase c. Okay, so let's take a look. Okay, so your mass is equal to 878.0, 4 significant digits, but that's not really all that precise. Well, actually it's milligrams, so that is pretty good. That's 1/10 of a milligram. So that's what we can do in the laboratory. And the temperature goes from, I'm just going to write this here, 56.3 to 68.2. Okay, so let's calculate our delta T. Right, if something's going from something to something, that's the final. So this is T final, and this is T initial. So T final minus T initial. So 68.2 minus 56.3. Let's see, if that were 68.3, that would be 12, right? So it's 11.9. Okay. And then the heat, they tell us how much heat it is, Q. They say it's 49.1 joules. And that could be done via electricity. You can often put a wire through a sample, and the wire you can, using electronic circuits, your cell phone does an amazing job of this, of measuring voltages and regulating voltages and currents. You can measure how much energy is flowing through the electrical circuit, and that'll tell you how much heat is produced. Okay. So there we go. So now the question is, what is the specific heat capacity? Okay, that's C, right? So Q equals MC delta T. We want to know C. So how do we do that? Well, we want C isolated on the right side. So I'm going to divide both sides by M. And then that's gone. So now you have Q over M equals C delta T, right? But again, we just want C, right? So we're going to divide both sides by delta T. Boy. There we go. So now delta T cancels, and you've got Q over M delta T is equal to C. All right. Now, when we do this, we're going to end up with milligrams per milligram. End up with per milligram, but that's fine. We'll do the conversion afterward. Maybe the answer could be in milligrams. We'll see. Okay, so let's take a look. So we have 49.1 joules. So I'm substituting in all of our values. So there's our Q. Our mass is 878.0 milligrams. And our change in temperature is 11.9 degrees C. Okay, so notice none of the units cancel, right? There's no canceling here. So it's just going to have those 3 units, but that's okay. Specific heat, we said, is typically joules per gram degree C. So let's go through the arithmetic. 49.1 over 878 over 11.9. I think they said they wanted 3 significant digits. So we end up with this very small number. I'll put a little dot there for times, right? 0.00470. I rounded it to 3 significant digits, right? Remember, leading zeros don't count, but trailing zeros do. Okay, so that's C. Now, that's probably not the units that Alex would prefer, because look how small that value is, 0.00. So I guess you could put it into scientific notation, but then you would have millijoule. Oh, let's do that. Here's I'm going to show you a technique. I'm going to move this into scientific notation, and that's going to give me 4.70 millijoules per milligram degrees C. Why is it millijoules? Because if I move the decimal place 3 places to the right, that's 10 to the 3. I'm sorry, 10 to the minus 3, right? Left is positive, right is negative. So 10 to the minus 3. 10 to the minus 3 is milli. So that's really 4.70 millijoules per milligram. And what happens? The millis cancel. So now you get 4.70 joules per gram degree C. So that's one way to approach it. Now, in a sense, we just kind of got lucky because the value was such that moving it 3 places to the right gave us the same prefix milli as we had in the denominator. So that's perhaps not the most, probably not the best way to do it as a standard method. So let's try it this way. Okay, so we have 0.00470 joules per milligram degree C. Essentially, the units typically are in joules per gram degree C, not joules per milligram. So we want to get rid of the milli. So what I'm going to do is I'm going to write 1 milli is equal to 10 to the minus 3. So 1 milligram is equal to 1 times 10 to the minus 3 grams, right? Okay, 1 times 10 to the minus 3 is the same as 10 to the minus 3. I like to write 1 times 10 to the minus 3 because when you use your calculator, if you just type in 10 to the minus 3, it sometimes gives you a messed up answer. But if you write 1 times 10 to the minus 3, it sometimes works a little bit better. Okay, and then we use that as a conversion factor. We're trying to get rid of the milligrams, so we're going to do it this way. To get rid of the milligrams are down here, so we got to put this milligram up here, right? That way they're going to cancel. And then 1 times 10 to the minus 3 grams. And that will get rid of milligrams and we'll have grams. So now just be careful. Maybe you want to use parentheses when you enter this into your calculator. So you might want to do like 0.00470. You're dividing, right? So divide and then maybe put this in parentheses, right? Just so that the calculator knows what you're doing. Okay. So 0.00470 divided by 1 times 10 to the minus 3, and you get 4.7. Remember, 3 significant digits. And then again, we're going to have joules per gram now, right? Joules per gram because we got rid of the milligram, and then we have times degrees C. Okay. There you go. That's pretty high. That is a pretty high specific heat capacity. I don't know what that substance is. Water is 4.8. Oh, so it might be something, it might be water with something else in it because water's 4.8. That's pretty close to 4.8. So it's probably water with something else in it. Okay. So there we go. Let's take a look at a second type of problem, very similar. A couple of these are very similar. Now, this one, you're going to see Kelvin in it. And I'll show you how to deal with that. It's not a big deal. It's just I put it in there for some reason. Generally, chemists don't use Kelvin for these problems. So let's take a look at this problem. Calculate the energy required to heat 256.0 milligrams of cyclohexane from 14.7 degrees Celsius to 20.0 degrees Celsius. So again, there's your delta T, right? There's your mass, M and delta T. Assume the specific heat capacity of cyclohexane under these conditions is 1.85 joules. Now notice the notation, joules times grams to the minus 1 times Kelvin to the minus 1. Round your answer to 2 significant digits. When you see those exponents -1 or -2, that means divide it. So it's really 1.85 joules divided by grams, divided by Kelvin, K for Kelvin. In these problems, you can substitute Kelvin for Celsius, perfectly fine. So you could write it. You can, in fact, I'm going to suggest you rewrite it as 1.85 joules divided by grams divided by degrees Celsius. Okay, so let's take a look at this problem. Okay. So the energy required to heat cyclohexane is 256.0 milli to, oh, I'm sorry. It's an issue of language. The energy required to heat 256.0 milligrams of cyclohexane. So the mass is 256.0 milligrams. The heat, Q, is 1.85 joules times grams to the minus 1 times Kelvin to the minus 1. This is just a notation. -1 means divided. So this is 1.85 joules divided by grams. And again, I'm going to put degrees Celsius. So here's my logic. The change in temperature of 1 Kelvin is equal to the change in temperature of 1 degree C. So the difference in temperatures in Kelvin is equal to the difference in temperatures in Celsius. So for that reason, we can just put divided by degrees C. Okay. The I'm sorry. Let me come back here. Because again, I made a second mistake here. I made a couple mistakes in interpreting this for you. Let's come back. Let's read this very carefully. Calculate the energy required. So we're asked for Q. We're not given Q. It says calculate Q. Required to heat 256.0 milligrams. So there's your mass. So we're asked to find Q given the mass. We are also given the two temperatures, which allows us, that gives us delta T. Assume the specific heat capacity is 1.85. So my mistake right there was saying that Q is 1.85. That's can't be the case. The units alone would tell you that that cannot be Q. Q is heat. Q is energy. Q should be in joules or millijoules or kilojoules. So I misinterpreted the readings. You have to be very careful. You have to write this. Essentially what they did was they asked you the question right at the beginning, and then they gave you all the information after. Okay, so now let's come back to this and we can retry it. Okay, so Q, we want to know what that is. We are given that the mass is 256.0 milligrams. We're given that the change in temperature, which is the final temperature minus the initial temperature, is 20 degrees Celsius minus 14.7 degrees Celsius, which we can just do that right now is 5.3. Okay. Takes heat to make something get hotter, right? So now assume the specific heat capacity is. So C is 1.85. And again, joules divided by grams divided by degrees Celsius. Okay. Now we want to find Q. Well, we come back to our equation here, MC delta T. 256.0 milligrams. Our C is 1.85 joules per gram degrees C. And then our change in temperature is 5.3 degrees C. So look at the dimensional analysis here. Okay. Degrees Celsius is in the denominator, so it will cancel with that one right there. The grams will cancel, but we're going to have milli, right? We can't cancel the milli here because this is not milligrams, it's just grams. So you can only cancel the grams. So our answer then is going to be in millijoules, which might be okay. So some problems, that's okay to have your answer in millijoules. I'll show you either way. Okay. Now it's 256.0 times 1.85 times 5.3, and it's 2510. Now that's a problem getting 3 significant digits there. So what you could do is you could put it into scientific notation, or we could get rid of the millijoules and convert it to joules. So let's try that. So let's convert to joules. Okay, well, 1 millijoule is 10 to the minus 3 joules. 1 times 10 to the minus 3 joules, okay? So let's convert it, 2510 millijoules. We want to get rid of the milli, so we want to put the 1 millijoule down here. And then 1 times 10 to the minus 3 joules. So millijoules cancel. And what you're going to get is 2.510. And then you'll have joules, okay? So now 3 significant digits is easy. 1, 2, 3. So 2.51 joules. So it actually is probably better to have it in joules in this particular problem than it is to have it in millijoules, okay? And there you go, okay? So those are the first 2 calorimetry problems. There's 3 more that we're going to go through, so we'll go through those tomorrow. So we'll wrap up calorimetry tomorrow, and then it'll have to wait, I guess, till next week. Yeah, it'll wait till next week. We'll do the last topic, which is standard enthalpies of formation. We're doing fine because this one is not due until the 24th anyways. So we'll on Tuesday, next Tuesday, we'll cover standard enthalpies of formation, and then we'll start getting into gases, which is the next topic, chapter 10. Okay. All right. There we go. Stop that. And have a great day.